This chapter is about atoms that are radioactive. Radioactivity, or nuclear reactions, begin with the nucleus. Remember that the nucleus is composed of protons and neutrons. And so, since we've talked about subatomic particles, we want to talk about the types of reactions they can undergo. First of all, radioactivity, again, is the decay of the nucleus, which results typically in the release of very high energy particles, usually accompanied by a high energy light. And again, all of this comes from the nucleus of an atom. The reason some nuclei or some atoms are radioactive is that they are unstable. Their nucleus is unstable, and that causes them to literally spit out parts of their nucleus until it's stable. So just some vocabulary. The starting radioactive atom is called the parent nuclide, and the daughter nuclide is what's left over after it spits out some of its nucleus. And it turns out that if you look at the periodic table, atomic number 84 and above are all radioactive, and that's because they have such large nuclei. Okay, so I don't know if you've ever wondered, but if you look at a nucleus, it has a bunch of protons, all with a positive charge, crammed tightly together. And like charges repel each other. So what on earth is keeping those positively charged elements right next to each other? And it's something called the strong force, nuclear strong force, that holds all of the subatomic particles together in the nucleus. That is actually the strongest force known to mankind. That's where the force of an atomic bomb comes from. So just to kind of compare and contrast, normal chemical reactions involve the electrons outside of the nucleus, okay? Nuclear reactions involve the nucleus. So we're going to talk about three primary types of radioactive decay and then a couple of more minor types. You may well have heard of alpha, beta, and gamma decay, so you should be familiar with these three. An alpha particle is a particle emitted by some radioactive atoms. An alpha particle literally consists of 2 protons and 2 neutrons. So if you have 2 protons and 2 neutrons, okay, it turns out that the overall charge is going to be plus 2. So the overall charge of an alpha particle is plus 2 because of the 2 protons, and a mass of 4 atomic mass units. Remember, protons and neutrons each have a mass of 1 AMU. And it turns out that 2 protons actually makes a helium. So an alpha particle is often referred to as a helium nucleus. Okay, beta decay is weird, okay? A beta particle is literally an electron, but it is not an electron from outside the nucleus. It's an electron that is formed in the nucleus. And you're like, what? We'll go over that in a little bit more detail, but it turns out that they come from from a neutron decaying. All right, so because they're identical to an electron, they have a charge of -1 and a mass of close to 0. A gamma decay is not a particle. It is the highest energy electromagnetic radiation or light that we know of, and it normally accompanies alpha and beta decay. All right, there are a couple more types of radioactive decay that I just want you to be somewhat familiar with, and that is positron emission. A positron is equal and opposite to an electron. So it's a negligible mass charged particle, but with a charge of plus instead of minus. And finally, there's a type of nuclear decay called electron capture, which is just the opposite of beta decay. It's when a nucleus snatches an electron from outside the nucleus and combines it with a proton to make a neutron. So let's talk about each of these decay in a little bit more detail. Alpha decay. Again, an alpha particle has 2 protons and 2 neutrons. It is a helium nucleus. So again, it has a mass of 4 and atomic number of 2. And one of the things you need to be able to do is to balance nuclear reactions. So the most important thing you need to keep in mind is that the mass and the atomic number for nuclear reactions has to be balanced on both sides of the arrow. Okay? So you see on the left side, the mass is 238. Make sure that when you add together the masses on the right side, it also is 238, and it is. And then you do the same to the atomic numbers, 90 and 92 add up to be 92. So everything's balanced here. And so if I were to give you, let's say, if I would have just given you this much of the reaction and said, okay, this undergoes alpha decay, you should be able to predict the products. And you have to remember, what is an alpha particle? You start with that. Okay, it's a helium nucleus, mass of 4, protons 2, and then simple math will tell you what the other substance is. It must have an atomic number of 90 so that atomic numbers are balanced, and it must have a mass of 234. So now, because the atomic number identifies the element, you look in the periodic table and find out what element has an atomic number of 90, and that is thorium. All right, so beta decay. Again, a beta particle, which is symbolized like this. Remember that electrons have a mass of about 0, and this -1, you'll see it a bit later, is because it has separated to form an extra proton, separated from a neutron, and you'll see that symbolism will help us balance the charge on both sides. All right, so again, how is a beta particle formed? It starts with a neutron, and a neutron in the nucleus decays to make an electron, which we call a beta particle, and an extra proton. So the parent nuclide ends up with another proton than it started with. So this is actually turning into a completely different element because of that. Because the beta particle has much lower mass, it can penetrate and is more dangerous, can penetrate deeper and is more dangerous than an alpha particle. So in conclusion, when an atom loses a beta particle, the atomic number actually increases by 1 because it's gained a proton. The mass number remains the same because essentially a neutron is turned into a proton and they have pretty much the same mass. And finally, gamma rays don't just occur by themselves. They're usually the form of energy from the strong force breaking apart when alpha and beta decay occur. It's usually accompanied by gamma ray emission. Because it's just light, there is no mass, no atomic number, just pure energy. Gamma rays are the highest form of light energy that we're aware of. They're the most dangerous because they're the most penetrating. You need either a thick chunk of lead or thick cement to protect yourself from gamma rays. Okay, and then the two more minor modes of radioactive decay. Positron emission. Again, a positron is simply the opposite of electron. And so now in this case, instead of with beta decay, we have a neutron decomposing. With positron emission, we have a proton that decomposes to make the positron and a neutron. So here's a good example of that. So you have lost a proton. So notice how we started with 15 protons, ended with 14 protons. So we've made a new element. And the mass has stayed the same because you've essentially converted a proton to a neutron and they have comparable masses. Finally, electron capture. This is when a nucleus snatches an electron, just a regular electron from outside the nucleus. It pulls it in, combines with a proton to make a neutron. So this is the complete opposite of beta decay. If you were to start with a neutron and go in this direction, it would be called beta decay. So electron capture is the opposite of beta decay. But what have you done to change the element? You have reduced the protons by 1, okay? And you have kept the mass the same. So here's a summary of all of them. It might be handy to print this one out. And I like that there's an example of all of them. So you need to be able to write balanced nuclear reactions for any of these types of nuclear decay. I'm going to do a couple practice balance reactions for you. I think we talked about this one already, but uranium typically decays in the first step with alpha particles. And you can either show an alpha particle as a helium nucleus, or sometimes it's just shown with the alpha symbol. So either way is perfectly fine. Again, you got to make sure that you can figure out what the daughter nuclide is by balancing the number of protons and mass number on both sides. All right, and so here's kind of a practice of all the different types of decay, and then I'll ask you to try to do some on your own too. So here's another example of alpha decay, and this would be a typical problem that I might give you. So I might say, okay, radium-224 decays by alpha decay. What product would it make? Okay, what is the daughter nuclide? And again, you would simply have to use addition to figure out 4 plus what is 224, okay? And 2 plus what is 88, okay? Once you find the new atomic number of protons, look in your periodic table, and in this case, it is formed radon. All right, beta decay again, you remember that that's when a neutron decomposes to form a proton and a beta particle. So you formed an extra proton. So your proton, if you start with 97, it's going to be 98. Okay, and here's the beta particle. Sometimes a beta particle will be shown with a B instead of an E. Either way is fine. And again, you figure out what the product is by making sure you do addition correctly. So notice that a beta particle has this -1, and that's so that your math works out right in these balanced equations. 98 minus 1 is 97. And so if you look 98 up in the periodic table, it's californium. Okay, positron emission. That's when you start with a proton and it decomposes to make a neutron and a positron, which is like a beta particle, only with a plus charge. So in this case, when you do your math, okay, it's +1. 7 plus 1 is 8. The element that has atomic number 7 is nitrogen. And finally, electron capture. That is the complete opposite of beta decay. So in this case, you have a proton in the nucleus combining with an electron outside the nucleus to make a neutron. So the number of protons goes down by 1 and the mass stays the same. Okay, so if you started with atomic number 53, you're going to end up with atomic number 52. Look in the periodic table, that is tellurium. So I recommend going through some of the worksheets, making sure you can do this. Here's one for you to try to work out right now. You'll want your periodic table, and I would recommend turning off the video for a couple minutes and working through these, and then I'll work them out for you and you can check your answer. Alrighty, hopefully you tried to work this out on your own. So the parent nuclide is radium-224. So the mass number goes in the upper left. Then you have to look at the periodic table and see the atomic number for radium. Whoopsie, I should have looked ahead of time. Let's see, what is it? Let's see, it's 88. All right. They told us it's alpha decay, and so we know that one of the products is the helium nucleus, and now we'd simply do math. So we know that the daughter nuclide has to have an atomic number of 86, because 86 and 2 is 88. And we know the mass has to be 220. So what is the atomic number that determines what element it is? Looking at the periodic table, and atomic number 86 is radon. Okay, that's it. Nuclear equation for the alpha decay of polonium. Okay, mass number of 216. And looking at the periodic table, its atomic number is 84. Again, they told us it's alpha decay. Whoop, plus. So mass has to be 212, and the atomic number has to be 82. And element 82 is lead. Okay, not hard. All right, so here is a little bit different way to ask the question. In this case, they tell you the parent nuclide and the daughter nuclide and want to know what type of decay it is. So again, I encourage you to turn off the video for a minute, see if you can figure that out yourself, and then I'll work it out for you too. All right, so potassium, mass number of 40, periodic table tells me atomic number is 19, and I'm going to form some type of decay particle. And the daughter nuclide is going to be argon with a mass that hasn't changed. So right away I know it's not alpha decay, right? And argon has an atomic number of 18. So what type of decay keeps the mass the same and actually loses a proton? If you look back at the chart summarizing the different types of decay, there could be two different types of decay going on here. You could either have formation of, or positron decay, which, remember, the positron is just like the electron, except it has a positive charge. So 1 plus 18 is 19. So it could be either positron emission or electron capture. So if it were electron capture, you would have to show the electron being captured as one of the reactants. So either one of those would be completely acceptable. Alrighty, so a little bit of theory about why some elements undergo nuclear decay. And you may remember in the beginning I said element 84 and above spontaneously undergo nuclear decay because the nucleus is so unstable. And so that is, let's see, polonium has atomic number 84. So polonium and all larger elements are radioactive. All right, so we talked about the nucleus being very, very dense with lots of positively charged protons crammed close together, and those protons are repelling each other. So it is the nuclear strong force that's holding them together despite the strong repulsion. It turns out, though, there is a point at which you get too many protons in a nucleus, and the repulsion force is just too strong, and it makes the nucleus unstable. Now, the neutrons help kind of dilute that, the repulsion of the protons. And the more protons you get, you proportionally need more neutrons to kind of spread out or dilute that repulsion. So there's something we call the band of stability, represented by this graph. And basically, it looks at the number of neutrons versus the number of protons. So obviously, the slope is the ratio of protons to neutrons. Okay, and so for elements 1 through 20, remember Z is the atomic number. For elements 1 through 20, the small elements, a stable nucleus is when the proton to neutron ratio is simply 1. So that's down here up to element 20. It's just a 1-to-1 ratio, okay? When you get a little bit larger, so for elements 20 through 40, the proton, oh, nope, I have it backwards, don't I? It's neutron to proton ratio. You want more neutrons. So neutrons is on top. So when you have a little bit larger atom, you want more neutrons to help kind of dilute that repulsion. So the stable ratio then is about 1.25. So now we're going from atomic number 20 to 40, and you can see that you want more neutrons. So essentially, the larger you get in the atomic number, the more protons you have, the higher the percentage of neutrons to protons needs to be. All right, and sometimes you can predict the type of radioactive decay that an element will undergo based on how many protons and neutrons it has. If it has too many neutrons, which can happen, just overall too heavy, then you will undergo beta decay. If you remember, that is taking a neutron in the nucleus and converting it to a proton and a beta particle. If you don't have enough neutrons, which is quite common, then you have positron emission. Again, that's when you have a proton that converts to a neutron and a positron. Alrighty. Okay, so I'm going to walk you through one of these. I'll walk you through A, magnesium 28, and then you see if you can do the other two on your own. First thing you need to do is figure out if a question asks you what type of decay, you have to figure out how many protons and neutrons it has to begin with, right? And what the ratio is. So we're talking about magnesium 28, okay? Mass number is 28. If you look at the periodic table, magnesium has atomic number of 12. And so how many protons? We have 12 protons, okay? And we have 16 neutrons, okay? So neutron to proton ratio, okay, it's greater than 1. And magnesium, if you remember, it said, let's see, if you have elements between 1 and 20, the neutron to proton ratio should be 1. So this has too many neutrons. So what does something do if it has too many neutrons? It undergoes beta decay. And that means you take one of the neutrons and it decomposes into a proton and a beta particle, which is an electron. So let's draw out what that would be. Okay, and so with beta decay, you actually end up with an extra proton. So our atomic number would be 13 now. The mass would be the same. Oops. And what element has atomic number of 13? That is aluminum. Okay, so there would be our reaction. So go ahead and shut off the video, for a couple minutes and see if you can work B and C. And then I'll work them out for you and check your answer. All right, so in problem B, we have 12 protons, and 22 minus 12 is 10 neutrons. And so our neutron to proton ratio, okay, it's less than 1. And again, for elements 1 through 20, we want this ratio to be 1. So we don't have enough neutrons, okay? We want more neutrons. We want fewer protons is another way to look at it. So how do we get rid of protons? A proton can decompose to form a neutron and a positron. Okay, and you probably have to go back and forth to that table until you do enough of these. So writing a balanced reaction for this is a positron, just like an electron, but with a +1 charge. And so we have lost a proton because it's decayed into a neutron. So now we have atomic number 11. The mass is the same. And what element has atomic number of 11? That is sodium. Alrighty. And molybdenum, atomic number 40. So if you remember, let's see, atomic number 20 to 40 is most stable with a neutron to proton ratio of, I think, 1.25, and greater than 40, neutron to proton ratio should be 1.5. So you want a lot of neutrons. This is a large element. So let's see how many we have. All right, so 102 minus 42 is 60 neutrons and 42 protons. So let's see, the neutron to proton ratio is 60 to 42, which is real close to 1.5, a little bit less than 1.5. So we could use more neutrons, need more. All right, so that's very similar to the magnesium problem. So it would be positron emission, which would mean you take a proton from molybdenum and it decays into an extra neutron and a positron. And so we'll write our positron here. And our new atomic number of the daughter nuclide is 41, and the mass is the same. And let's see, what element has atomic number of 41? That is nobium, NB, nubby. Alrighty, that kind of gives you a handle. Again, I recommend working through worksheets of this to get more practice. All right, this is I've always thought this is kind of odd. There are some what we call magic numbers, and some rules that the nuclides are particularly stable. So even numbers of protons and electrons are more stable. So if you have, like, let's say 20 protons and 20 neutrons, or 18 protons and 18 neutrons, that is more stable than, for example, 21 protons and 21 neutrons, okay? So if you have either an odd number of neutrons or an odd number of protons, even one of them being odd, it is less stable. All right, so the magic numbers, and you don't need to memorize these. I just want you to be aware they exist. So if the total number, a nucleon, is anything in the nucleus, so it could be a proton or a neutron. So if the total number of protons and neutrons are any of these magic numbers, the nucleus is particularly stable and you won't see it undergo nuclear decay. All right, and finally, every now and then I've seen a question of these, particularly on the final. We have something called natural decay series that happen spontaneously in nature. And so one of the common ones starts with uranium-238. And so if you wanted to follow one of these, if somebody gave you a graph and asked you to interpret it, that's all I would expect you to do. But uranium-238, in its first decay process, so would you be able to tell me what type of decay this is, going from uranium-238 to thorium? Hopefully you can see that is alpha decay. And then going from thorium to uranium-234 would be beta decay. And so this is a natural decay series. And just be able to recognize that when the number of protons is decreasing, so the arrow's going to the left, okay, and at the same time neutrons are decreasing, the arrow's going downward, that's alpha decay. So all of these are alpha decay. Okay? And then again, if you're increasing protons, if your arrow's pointing to the right, that is beta decay. That's it for this lecture.